Yes, class. Am I audible to all of you? Good evening, Rasita. It's a continuation of first lesson only today. I told you, no, that we'll be completing the first lesson this week, and next, from the next class, we'll be starting the next lesson. All right, second lesson. So this has to be most probably the last class of the first lesson. Let us not waste our time on this discussion. Let us quickly complete and start with Gauss theorem. I want to start Gauss theorem today. See, electric flux was what? In the last class, I have discussed with you yesterday that electric flux is basically number of field lines which are crossing per unit area normally. Fine, only you will consider the field lines which are perpendicular to the surface. Now, once the field lines are going, once the field lines are moving, every time it's not possible to manually count the electric field line. So what we do, we have a particular formula for the same. Phi is equal to E dot S, that is ES cos theta. This is the formula, and regarding this formula, we started one or two questions we discussed. One question was left from this topic. See, electric field exists in space. This is given in Cartesian form. Area is given as 5 meters square in XY plane. So in the two questions which we did yesterday, look, what's the difference with this question? We discussed here, everything was given in polar form. Here, everything was given in polar form. Polar form means in 11th class, you must have studied this in your basics. Polar form means between the vectors, angle is given. So here we had the angle that was 60 degree between the vector and the plane. So we calculated the angle that is required by us. That is the angle that is made between the magnetic field line and the area vector. So we got our theta. So electric field is equal to ES cos theta. Phi is equal to ES cos theta. That is valid over here. We could calculate it. In the second question which we discussed yesterday was both electric field as well as the surface area. They were given in Cartesian form. So first question polar form, second question Cartesian form. So here we didn't require any angle because we just simply could take the dot product of both the same. Now the third question which has been mentioned to you, which I want to discuss with you is that, see, electric field is given. And class, please pay attention over here because as it is, it will come. The way you are having electric flux in magnetics, you will have magnetic flux. Electric field line, magnetic field line. Same types of questions will be there. So get your concepts cleared over here. That time we will not take so much of time. I am devoting so much of time in this lesson as well. First lesson and second lesson, I'll take time. Why? Because all the concepts that will be built over here, then only you'll be able to rush up with the syllabus for the upcoming lessons. These are your basic lessons. Just clear them very well. Electromagnetism's core topics are these. And electromagnetism is your complete first book. That is half of your syllabus. Right? Then you have optics and some lessons of modern physics that are easy. You will be able to manage them at the end. But once this is unbalanced by all of you, then you will not be able to balance the second book as well. If this is strong, then the second book will help you score well. Now see, electric field is given. This is saying calculate flux through area 5 meters square. Now see class, angle is also not mentioned, and the Cartesian form, Cartesian values, the unit vectors of 5 meters square, that is area, is also not mentioned. At least we cannot simply multiply 5 with I cap plus 2j cap plus 3k cap. No, you have particularly, see, electric field that is mentioned to you is I cap plus 2j cap plus 3k cap. You have to have a proper vector. Otherwise, you cannot multiply 5 with I cap, no, without any I cap, J cap, K cap's value. And angle is also not given. Now, how we'll solve this question? So, in this question, this has mentioned to you what is the hint that is given to you is the Cartesian form of area is mentioned to you. See how the Cartesian form of area is mentioned to you. Look here. Electric field is given. Let me show you. Suppose this is the surface area that you are having. This is the plane. Electric field lines are crossing. Now discussing the planes. This plane that we get, this is our XY plane. This is the y-axis, this is the x-axis. So between x and y, we are getting xy plane. You must have studied motion in a plane in the last year. So motion in a plane occurred here. So similarly, this is your plane, XY plane. Then we shift it. This C here. This is Y axis. This is Z axis. So this is YZ plane. XY plane, YZ plane. Now coming to this is the x-axis and this outwards, pointing outwards is the z-axis. So this plane is XZ plane. Now when the question is saying calculate flux through area of 5 meters square in XY plane, it means you have received your plane. Your plane is this XY plane, y-axis and x-axis. So this is the XY plane. Coming to electric field, coming to your Gauss theory, your electric flux. How do we calculate the electric flux? We have studied yesterday how we calculate the electric flux. We have to have area vector. I have told you that it is the prime condition of it. How do we take area vector? For area vector, we just drop a perpendicular on the surface like this. Now, the perpendicular is pointing to which axis? If this is the XY plane, this is pointing in the which axis this is pointing in? XY plane, this is pointing in the Z axis. Because perpendicular to XY plane will be Z axis. Suppose instead of XY plane, the question gave you YZ plane. So perpendicular to this would have been X axis. ZX, XZ plane. Perpendicular to this would have been Y axis. So right now XY plane is given. So perpendicular to this is Z axis. And for Z axis, we use the unit vector K cap. I told you, I cap is for X axis, J cap, Y axis, K cap, Z axis. Depending upon positive, negative, put in the signs as positive and negative. So electric field that is given to you is I cap plus 2 J cap plus 3 K cap. So surface area will be 5 K cap. Why K cap? Because this is telling you the unit vector. This is telling you the area vector. Area vector is perpendicular to the plane surface. Yes, this is perpendicular to your surface. Now you will calculate flux. Flux is simply E dot S. Electric field is I cap plus 2 J cap plus 3 K cap. Dot product with 5 K cap. See, when I write 5 K cap, that means 0 I cap, 0 J cap. That's why I'm just considering 5 K cap. So 0 multiplied to I cap, no coefficient of I cap. There is no coefficient of J cap, it means 0 J cap. So this is 0. 3 from here multiplied to 5 from here, that gives 15 Weber. That's it. So what you had to do, see, the question was very simple. What you had to remember, you just had to remember this 5K cap. That's it. The questions are solved. Now, one very important question I have to discuss with you. Quickly note it down. I'll discuss. See, why are we getting 5k cap? The reason is that your plane is xy plane. And whenever we use calculations for electric flux, we include the area vector n cap. Remember, in the last class, I told you even if angle is given with respect to the plane, you won't include it. You will calculate the area vector. So how will you take the area vector? Nothing is mentioned, but one thing that has been mentioned is the plane. So if you know the plane, how can you calculate? If you know this plane, perpendicular to the plane will be the area vector. So xy plane perpendicular is z axis, and z axis unit vector is k cap. Clear, Fadil?
Yes, ma'am.
All right. Have all of you written this?
Yes, ma'am.
See, Mariam, the entire equation that you are having over here, this equation, this is actually if 5k cap is only written. So it's like 0 I cap plus 0 j cap plus 5k cap multiplied to I cap plus 2j cap plus 3k cap. So 0 I cap multiplied to 1 I cap. This is 0. 2j cap multiplied to 0 j cap. This is 0. Now we are left with 3k cap dot 5k cap. See, k cap dot k cap is always 1. So what are we left with? 3 into 5 is 50. Clear?
Yes,
See, this I was mentioning that if we are taking, see, whatever surface area is given to you, if surface area is not definite, like that has been mentioned right now, like equation of surface area is not mentioned or some other equation is not mentioned, so what you will do? Whatever is the actual surface area, you will consider it that. For example, you are having a sphere, so you will take the surface area as 4 pi r square. If you are having a cylinder, so you will take the curved surface area, that is 2 pi r a. All right, just remember this point as a note point. You can write it down later. Now this question says that charge Q is placed at the center of a sphere. Calculate the flux through it. See, again, we require, see, electric field is being produced. We'll take n cap also. Now coming to our flux, we know flux is closed integral of E dot ds. Yesterday in the last class, I have told you that whenever you are having a curved surface, we take ds. ds is what? ds is infinitesimal small, very, very small surface area. Yes, that we take. Now, when we are integrating EDS, what is the surface area you will consider? This is what I was telling you just above this, that you will consider the
4 pi r
entire
square.
surface. Priya, you are asking something?
Yes, ma'am. 4 pi r square.
Oh, yes, 4 pi r square. Very good. Surface area, this is ds is 4 pi r square. This is right. And electric field. Priya has answered what is the surface area. What about the electric field class? Electric field due to a sphere or electric field due to a point charge we have discussed.
KQ by R square.
Very good, Fadil. KQ by R square. Good. So this is K. Charge is already given as Q. Radius is R square. Let me write K as 1 over 4 pi epsilon naught R square. So we have E with us. We have ds with us. This is very important. Why? You will just understand. This question doesn't seem so difficult, but it has a lot of significance. Why? See, let us put both the values. Q by 4 pi epsilon naught r square multiplied to 4 pi r square. 4 pi will be cancelled, r square will be cancelled. Phi is equal to Q by epsilon naught. Now the result which you are getting in this question, this result, Q by epsilon naught, this is actually Gauss law. This is known as Gauss law. What is Gauss law? According to this Gauss law, if you are having a closed surface, some charges are present. There are charges which are present within this, the enclosed charges. So according to Gauss law, whatever answer you, this is also a proof of Gauss law. If it comes, no, proof Gauss law. So this is a proof of it. How you will get it. Or derivation also you can say. So what does Gauss theorem says that? It says that if a closed surface is present, the flux, the net electric flux, this will be equal to 1 by epsilon naught times the total charge that is enclosed within the surface. You will not include all the outer surfaces. What is epsilon naught? It is the absolute permittivity of air, that is 8.85 into 10 to the power minus 12 that we see. What are all the properties of Gauss law which you have to keep in mind? See, it does not depend upon the different shapes or sizes. If I'm having this, still my flux will be Q by epsilon naught. Double the radius, still the flux will be Q by epsilon naught. Shift it, make it into the form of cylinder, flux will be Q by epsilon naught. Just a random sphere, this random surface, this will be Q by epsilon naught. So flux does not depend upon the different sizes or shapes. It just depends upon the charge in enclosed. When I say enclosed, suppose these are the charges present, you will consider this, the net charge enclosed, it will be Q1. You will include this minus Q2. You will include this plus Q3. You won't include these two because they are not included, right? So what will be your flux? This will be Q1 minus Q2 plus Q3 divided by epsilon naught. Though the charges are present, you will not consider. This is a very important law that will be staying throughout and class. Some topics are there which you have to revise at any cost. This is one of the topics with which I can say you can start your preparation with, or if you're having a very less time and you want to revise a very prime important topic from the lesson, this is the topic which you can. Gauss law. Gauss law, if you are having your unit test, then definitely from Gauss law questions will come. Definitely, that is for sure. But if it's a mixed question from the entire lesson, chances are there that you will get the questions more from Gauss law. And what we did study in the electric field lines, that if it's a positive charge, field lines are moving away. So outwards flux is taken as positive for positive charge. This is valid for a positive charge. So outward flux, electric field lines are moving away. So it's outwards flux. This is positive. And opposite, this is negative charge. For negative charge, you take the inwards flux. This becomes negative. So just keep these things in mind. Last 2 points which I want to discuss. See, if a surface is there, suppose this is a surface. Flux is what? Flux is number of field lines which are crossing an area normally. Fine. So number of field lines which are crossing. Crossing means something has to be passed. Suppose this is the surface. Something, if it is going within this, something is going within this, then only I'll say, no, it is crossing. If I say that this is something is just passing like this, if this is a field line which is passing, it's not intersecting it, it's not touching its surface. Fine. So what will I say about it? No flux is present, right? Because no field line is crossing it. So phi becomes 0 in this case. Now, one more thing, a way which, how can you define this is that, see, if field line is just crossing it, see, if field line, suppose field line is just crossing it like this, it's just crossing it. This is not, is just passing through. It's not actually intersecting it. It's just passing by. This is not going inside it. This is not penetrating. This is just crossing like this. Now consider the n cap, area vector. Area vector is perpendicular. What is the angle that is now being made with the electric field line and the area vector? What can you say? What is the angle that is
Theta.
being? How much?
Theta,
90,
ma'am.
ma'am. 90
90
degrees.
degree. Yes, 90 degree. See, suppose the magnetic field line is at a certain angle like this, some random angle. Then we take the area vector and then we calculate, when we take the area vector, we calculate this angle. This is what I've told you, no, the angle between the area vector and the electric field line. This angle we consider. But if your electric field line is like this only, and now you are taking the area vector, so what will happen? The cos theta will automatically become 90 degree. So what will happen? Theta is 90 degree over here. So phi is equal not be E. Phi is equal to ES cos 90 degree. Mathematically, this is how you can show. Physically,
Ma'am,
this
so in this case, it's not going inside. It's just
it's
passing
not
by.
going inside. Yes, this is one case. And one more case that can happen where no flux is present is a case of dipole. See, in case of dipole is a set of charges which are opposite in signs and equal in magnitude. So net charge will always be plus Q minus Q. They will always be zero. If your Q enclosed is zero, always your flux will be zero. So flux will be zero always in these two cases. There are no exceptions in these. Fine. Note down this entire Gauss theorem. We'll practice one question also based on this. Note it down from here, make a note point. And whatever doubts you are having in between, best way is that write it in the chat column, wherever you're getting stuck, or unmute yourself and ask.
Ma'am, can you scroll up?
See, Fadil, the derivation which I told you, no, the question which you did, that is not actual derivation. Otherwise, I would have not written it as a separate question. I would have directly written it under the Gauss theorem, under Gauss law, the way we did other questions, other topics. Here, this is just an example to prove Gauss theorem. Gauss theorem is done experimentally. This was done by Gauss experimentally, and the conclusion to it was Q by epsilon naught. Now, when you're talking about a sphere, you have a different derivation for it. When you are having a cylinder, you are having a different derivation for it. You apply Gauss law, you apply Gaussian surface. We will see there are different surfaces, and for every different surface, there is independent values of derivation. So that's how you can say different, the shapes are independent on it. When we come to the fact regarding the sphere question which we did, so that's a separate question. But in your exam, if the proof is that this is just a proof, you can prove anything with any example that you have. So this is a relevant example which you can use, and it's a very easy one. There are other also forms of the question which you can use. For cylinder, you have an entire separate derivation. But how many derivations will you be able to remember? For how many shapes? Because this was actually done experimentally. That's why we do not have a proper derivation for it. But just in case in your exam, if proof is asked, so how will you prove it? So for the proof purpose, I told you that take it as a derivation. This is not a standardized derivation of Gauss law. Otherwise, I would have written it under this heading. Clear, Fadil?
Yes, ma'am. So, ma'am, even if we were to prove it using other shapes, would we get the same equation eventually?
Yes, yes. For all the shapes, we will get this equation. That's why
Okay.
I'm telling you, this is actually the conclusion based on whatever experiments you do. So for
Okay.
every shape, ultimate answer will remain this.
Okay.
Done?
Yes, ma'am.
See, class, the next topic that we have to start, some of the portions of Gauss theorem only. This is the last topic only. It's just that in certain derivations, like I was mentioning to Fadil also, you will have certain figures, you will be having specific objects, and there for them you have the Gauss theorem derived. So for them for that you have to understand continuous charge distribution. So let us just complete that first. Continuous charge distribution, because it will be used throughout, and somewhere you will find the questions are also written separately. So what is meant by a continuous charge distribution? Firstly, we'll talk about linear charge distribution. Linear charge distribution, this is a very easy topic. We'll not waste a lot of time in this. Quickly, we'll try to complete this. Total length is L, charge distributed is Q. So linear charge distribution means on the entire length, when I talk about unit length, how much charge is distributed in 1 meter. Suppose this is 1 meter. For example, this is 1 meter. So how much charge is distributed in this? So in 1 unit, how much charge is enclosed? So Q is the charge uniformly distributed, L is length of wire. So this linear charge distribution, this is represented through the symbol lambda. Fine, lambda is written. So everywhere you will find lambda only written. So this is a standardized symbol. All right. So you can always use lambda. This is not that I have used or I want you all to use it in my class. NCRT, this is a standardized symbol. So linear charge density is basically charge per unit length. So charge per unit length will be what? Lambda is equal to Q by L, that is charge divided by length. SI unit will be coulomb per meter. If it is variable, if the distribution is not uniform, like this is your length, some charges are present here, some are less in this 1 meter, some are more in this 1 meter. So for that you differentiate it, dq over dl you use. Otherwise Q by L is simple. Let's see basic questions from this. This is not difficult to understand. See, charge of 10 coulomb is uniformly distributed on a wire of length 5 meters. Calculate linear charge density. Linear charge density, lambda is charge per unit length. Charge is 10, this is 5, that becomes 2 coulomb per meter. Now charge on 2 meter length of wire. See class, what is lambda? Lambda is 2 coulomb per meter. This means for 1 meter you are having 2 coulombs. Yes, for 1 meter you are having 2 coulombs. When I say lambda is 2 coulomb per meter, this means for 1 meter I am having 2 coulomb of charge. So for 2 meter length of wire, I'll have 2 into 2, that is 4 coulomb of charge. For 1 meter, if it's 2 coulomb, so for 2 meters it will be double of it. Yes. So that is the answer to this question. But the other that I was mentioning you, the variable part, like lambda is equal to 2x. And now if I have to find out the charge on 10 meter length of wire, so how will I solve it? See, lambda is equal to dq over dl. Yes, I have to find out the charge. So charge will be lambda into dl. So I'll integrate both of them. This is from 0 to total charge Q. This is from 0 to length is 10. Put the value of lambda, not 16, this is 10. Put the value of lambda, this becomes Q. Lambda is already a constant, but let's put its value. So this becomes integration of 2x. Let's take this as dx because dl, or otherwise you'll have to take this as length. Let's take the length as x, then only you'll be able to solve it from 0 to 10. This is a rule of integration. I hope you know that both the variables should be same. When you cannot make it, you can not directly. This is just a variable that I have chosen, dl. So for this question, I can make it as dx. If it was written 2l, I could have used dl. Now integrating it, q will be 2 will be taken common. This becomes x square by 2. 2 will be cancelled from 0 to 10. That is upper limit first minus lower limit. So that is 100 coulomb. This is the charge. So this is the first one, linear charge distribution. Write it down, then we'll go to, this is in one dimension. Then we'll talk about 2D, then 3D. See, who has asked this? Mariam. In this question, no, what we have done, lambda dl we have taken. So dq is equal to lambda dl. According to this formula, what will happen? This will get multiplied over here, right? Now q is equal to integration of 2x dx. So how do we integrate? Whenever you are having x to the power n, this becomes x to the power n plus 1 divided by n plus 1. Fine. So if the power is n, here the power is 1, x to the power 1. So that became 2 divided by n plus 1, that is 2. And we already had this 2. Now the next rule of integration says that whatever is the upper limit, that gets substituted in place of this x and then minus the lower limit. So 10 square minus 0 square. So 0 square is 0, this is 100. Just revise integration once. This is just the basic question from integration. It will be clear. Right now, is it clear?
Yes.
Okay, next is superficial surface charge distribution, you can say, or superficial charge distribution, you can say. So this is in 2 dimensions. 2 dimensions means when we are talking about area. Right now we were talking about length throughout when we were talking about the first one. Now what will happen in surface charge density? You have the area. So surface charge density is charge per unit area, not the length. So we represent it with the symbol sigma. Lambda was for linear. This is for surface charge density, sigma. So SI unit is coulomb per meter square. Meter was just for the lambda one. This is for sigma's SI unit is coulomb per meter square. And same thing, dq over ds for non-uniform. So this question says that a charge of 10 coulomb uniformly distributed on the sphere of radius 2 meter. See, charge, what is surface charge density? This is charge per unit area. Charge is 10 coulomb. Area of a sphere is 4 pi r square. So that becomes 10 divided by 16 pi. This becomes 5 by 8 pi coulomb per meter square. Now charge on 2 meter square area. Again, if second part means if sigma is 5 by 18 pi coulomb per meter square, this means in 1 meter square you are having 5 by 8 pi coulomb of charge. So in 2 meter square, how much you will be having? 5 by 8 pi multiplied to 2. That becomes 5 by 4 pi coulomb of charge. Clear? Similar question to what we have discussed. Last one is volume charge. Let me discuss this also, because this is also very easy. Once you have understood the first one, the other ones are easy. This is in 3 dimensions now. Length, breadth, height. Volume comes into action. So charge per unit volume. We represent this through symbol rho. Lambda for the first one, linear charge. Sigma for the superficial or surface. Volumetric or volumic or cubical charge distribution. All the names are same. Cubical also is used sometimes. All right. So this is charge per unit volume. So one more dimension gets added, that is coulomb per meter cube. Fine. So rho is dq over dv. So a charge 10 coulomb. Now you are having radius as 3 meters. So rho will be charge per unit volume. So charge is 10. Volume of a sphere is 4 by 3 pi r cube. Yes. So see, this 3 will go upwards. 3 into 10 divided by 4 pi into 3 cube. This 3 and the cube will become square. So this will be 10 by, where was it? Yes, pi. And here we are left with 9. Here you are left with 4. So 36. Or wait. Let's write it like separately. Let's write it like this, because we have to cancel it. Now charge on 3 meter cube of volume. This is coulomb per meter cube. Second part. We can do the second bit using the formula of area charge density or volume charge density as well as. What, Fadil? Second bit? Second,
Ma'am, the second bit in both of the questions.
where we have to calculate the charge.
Yeah, so we can directly apply the formula as well, right?
Yes, you can use the formula as well. You can
Okay.
simply multiply them also. Yes, you can use it.
Yeah. Okay.
So it's just that here charge on specifically 3 meter cube is asked. Right here, charge on 3 meter cube volume is asked. So for that also, no, same thing is occurring. See, if you are multiplying this, you require this. How will you get this? This is this. We are doing the same thing. We are also ultimately multiplying this. So it's actually the
Yeah.
same. Okay.
Right.
So it's like in 1 meter cube, we are having 10 by 4 pi 3 into 3 coulomb per meter square. So in 3 meter square, see whether you multiply rho into V or here also rho into V, we are doing 10 by 4 pi into 3 into 3 into 3. This 3 will get cancelled. So you directly have 3 by 12 pi. Or you can further reduce it. This becomes 5 by 6 pi coulomb of charge. This is surface charge distribution. Sometimes this is written as superficial charge distribution also. If this term is mentioned, don't be confused. This is the same thing. All those who have completed till here, you people can start leaving, attempt your after class assessment. So next weekend, we'll start with the new lesson. A little portion of this is left. It will take half an hour, but then in the next class only, we'll start with a new lesson. Thank you so much, class.